All right, welcome back. So in this video, we're going to talk about situations where instead of the price being lower when you buy small quantities of an item, the price is going to be lower when you buy larger quantities of the item. So we'll call this bulk discounts or concave kinks, which essentially means instead of having a budget constraint that bulges out away from the origin, it kind of sinks in towards the origin, which is fine if that's not very helpful. So as an example of this, let's imagine that you go to the farmer's market, right? You've got $15, and you can either buy apples or bananas. We'll say that the price of an apple is going to be $2 a pound. The price of a banana is going to be $1 a pound. Cool. Now, there's a special at the farmer's market. If you buy more than 5 apples, then the price drops to $1 a pound, right? There's a special. If you buy more than $5 a pound, every additional pound only costs you $1. Cool. So let's think about what this is going to look like, first of all. I'll just put apples up here, and I'll put bananas down here. So just like before, right, what we're going to want to do is we're going to figure out the intercepts, right, how many apples you can buy, how many bananas you can buy, and then we'll want to figure out the kink point. So let's start with the intercepts, right? Let's start with the banana intercepts because that's the easiest. Right, in that case, you've got 15 bucks, and they're $1 a pound. So you can buy 15 over 1 is 15 bananas. Right, how many apples you can buy? Well, we can do the same thing we did for the convex kinks, right? So we can think about how many apples does it take to get you to the kink point, and then how many can you buy with the leftover money. So your first 5 are going to cost $2 each times 5 is $10. That leaves you with 15 minus 10 is $5, right? And then they're $1 each from there. So then 5 divided by 1 is 5, right? So total, you can afford 5 plus 5 is 10 apples. Sounds good? Right, so 10 apples, 15 bananas. Now we just need to find our kink point. Our kink point is going to be where we bought 5 apples. So 5 apples, right, at a cost of $2 an apple. So 5 times 2 is 10. So that leaves us 15 minus 10 is $5 for bananas. And 5 over 1 is 5 bananas, right? So our kink point is going to be where we've bought 5 apples and we've bought 5 bananas. Cool. So what does that mean our budget constraint is going to be? Well, as before, we're going to have 2 pieces, right? We're going to have a blue part and a red part. We'll have a blue part like this, and then we'll have a red part like this, right? And the slope is going to depend on which piece of our budget constraint we're on. So here, once we've bought enough apples to take advantage of the bulk discount, we'll have PB over PA is going to equal 1 over 1 is 1. And then here, PB over PA equals 1 over 2, right? It's 1/2. Cool. And much like with a convex kink, right, when we have a concave kink or a bulk discount, we can think about this as really being like 2 different normal budget constraints, right? A red budget constraint and a blue budget constraint that just continue past the kink point. Now, the difference, and this is really important, is that whereas with a convex budget constraint, we kind of had to solve both of these 2 imaginary budget constraints, right? The areas on our dotted lines were not affordable for us. In this situation, it's really either or, right? If we had some spot that wasn't really in our budget constraint, it was on our fake blue budget constraint, that's affordable to us, right? So is a spot that's not really on, but looks like it's on our red budget constraint. And as a result, the way that we're going to go about trying to solve this problem is going to be by essentially solving our blue budget constraint, solving our optimal choice on our blue budget constraint solving our optimal choice on our red budget constraint, and then seeing which of those two optimal choices we like better. So I want to talk a little bit for a minute about why that's necessary and why that makes sense. And the thing to realize is we can have an optimal choice on, let's say, just our blue budget constraint and have it not be our best choice overall. Right? In this case, this point here looks optimal from the perspective of the blue budget constraint, where it's on the budget constraint, MRS equals the price ratio, but there's something affordable that's better than that choice, right? Anything that is above this indifference curve but below our red budget constraint is going to be better than that choice. And the reason why this is possible is normally, right, MRS equals price ratio is sufficient to make sure that this can never happen, because our price ratio is constant and our MRS gets lower and lower and lower as we move towards more horizontal good and less vertical good, higher and higher and higher as we move towards more vertical good and less horizontal good. Right? So in an ordinary problem with a straight budget constraint, right, if we know that our MRS equals our price ratio here, we know that it's got to be above our price ratio everywhere in this direction and below our price ratio everywhere in that direction. Right? So the fact that it equals our price ratio here is sufficient. In this case, though, because our price ratio changes, right, we essentially have a problem where while our indifference curve is bending away from our budget constraint is bending towards our indifference curve. So in this case, we might have our optimal choice on the first budget constraint here, our optimal choice on the red budget constraint here, and then how would we decide which of these is truly our best choice? Well, we want to pick whichever is on the highest indifference curve, and the highest indifference curve means the highest utility value, right? So the essential approach is, first, solve each budget constraint, and then B, pick choice, solution with highest utility value. Cool. And that's really what you do. It's exactly the same thing if we're thinking about interior solutions or corner solutions, right? If we found a corner solution here on the blue budget constraint, we'd still want to compare it to our best choice on the red budget constraint. All right, fantastic. So in the next video, we're going to move from thinking about specific individual optimization problems to thinking about how to use optimization machinery to solve for individuals' demand curves and what we're going to call individuals' angle curves, which is talking about how do our optimal choices change when our income